let you guys know just so I can put this on YouTube at that point. So afterwards, so if you want to go and review this afterwards or anything like that, I'll also share my whiteboard with you guys too, and put that up there also. Yeah, so if you have any questions, you can either put them in the chat, either during when I'm doing a problem, or if you want to ask a question, feel free to just unmute yourself and go for it. Anything that you want to talk about, we can absolutely do overall. So yeah, who wants to start? Feel free, anybody who wants to start, just unmute yourself or ask a question and go for it.
Could you review parameterizing curves just in general? I really struggle with that.
Parameterizing curves in general, sure. Let me pull up a whiteboard really quickly. Everybody can see this whiteboard? Okay. So just in general, let's think about what the idea of parameterizing. So parameterizing curves, there's really three big types. Honestly, there's really three big types of parameterizations that we really need to know just in general. So the idea of a parameterization is that I can explain all of the points x, y, and z on a curve with just one parameter. We usually denote this as t, but this can be any parameter, any letter you want, any symbol that you really want to use. And we can kind of denote this if it's in three variables, if it's in three dimensions, we can have z of t there. And we usually have this kind of domain here, that's a to b. Okay. And so what we try to do here is we try to find how can I tell somebody or my problem, how can I tell it to express all of the points on my line or my curve with using one single variable. We can always do this, which is really, really amazing. And we can always do it. Might be very complicated at some points, but we can always do it. And they really follow three tracks. There's really three flavors, I guess you can kind of put it, of these kinds of ideas. The first one is if I just have a function in the form of either y is equal to f of x, or of something like x is equal to maybe a function of y. Something like this. If I get an explicit function, for instance, as an example, you can maybe get something like y equals x squared here. Or maybe over here, you can get something like x equals y to the third plus 1. Something like that. Maybe I can actually do something a little better. Maybe cosine of y. Something like that. So what I have here is an explicit definition of what x is equal to in terms of y, or what y is in terms of x. I can get this explicit definition. Now, how could I explain, for instance, in this one, in this idea, I want to explain all the coordinates, right? I want you to give me one coordinate. I want you to give me one variable, a parameter, that gives me identification of where the x and y are. In this case, it's actually pretty nice, because what we can do is if I tell you the x coordinate, in this case, I can tell you the y coordinate very quickly. And so what we can kind of say here is in this general idea, I can let x be equal to t. This is my parameter, and y is equal to my function dependent on t. Now, why would that be? Right? So I could write this parameterization then as t comma f of t. Or in this exact case, I could write this maybe as t and t squared. And why does this tell me, why does it give me this, right? Why does this tell me it, right? It just tells me here, if I give you the x coordinate, I can tell you the y coordinates by plugging into f of t. Similarly over here, I have x as a function of y. And so you kind of maybe want to manipulate that to flip the idea there. So maybe I could tell you that y would be equal to t here, which would then give me what x has to be equal to. In this case, it would be g of t. And so you could write this maybe as r of t is equal to g of t comma t. In this exact case, right, I could say that this is cosine of t and t. Here. Now, the domain here is highly dependent on the problem itself, because it depends on where you're going. At least in this case, it's going to be dependent on the x coordinate. So if I tell you that x runs from -2 to 2, t will run from -2 to 2. And similarly over here, you could do the same thing. That's really the first concept there, if there's a function. The second concept, really the second part, is if I have a circle. If I have a circle, we know we have something of the form maybe x squared plus y squared is equal to a very general a squared. Why don't we go with that case? And if I tell you this, right, what I can then tell you is, okay, well, if I want to try to find, my goal again is to find variables, a variable that can describe what's happening all the time on this curve, right? If I have a circle, what's important to note is I'm always on a radius, right? I'm always on that radius specifically. I'm always on a circle of radius A, or something like this here. I'm always traveling around that area. And what's important to note here is you're like, okay, well, if I have a circle, you might think about polar coordinates, right? Polar coordinates can be described pretty well as x equals r cosine of theta and y equals r sine of theta. And what's important to note here is on this entire circle, I usually have that my r is constant. My r is always a. So what I could do is I could replace this with an a here and an a there. And then we could realize that what's actually changing is this theta component. The theta component is the only thing that's changing. And this is in a counterclockwise direction. If you're going clockwise, you have to manipulate this a little bit, kind of flipping the x and y there to kind of move it in an opposite direction. But for right now, let's just tackle this at least. That kind of is a different part. That's not really important here at this moment. So what this tells me, and then the theta would be between, you know, some value, depending on where I am. For instance, if I'm going from here to here, maybe, if I'm going from here to here, right, maybe I would use pi over 2 to 3 pi over 2. Something like that. And so what you could then say is, I could tell you my domain then, my parameterization could be something like a cosine of t, a sine of t. And then my t would be between, you know, two values, maybe theta 1 and theta 2. And t is dependent on theta now, right? It is because it is theta, just in general. So we always have to make sure, and this is actually a really important point, especially with circles, that this inequality makes sense. I know this sounds silly, but why does this inequality make sense, right? So if I have down here, I need a lesser number and I need a greater number up here. So just make sure that you're always, if you're going in a counterclockwise direction and maybe you're crossing this threshold right here where this is 0 and 2 pi, make sure that you maybe use either the negative version or you maybe go from like 3 pi over 2 to 5 pi over 2 or negative pi over 2 to pi over 2, something like that. And lastly here, we have one last one, which is a line segment. I am not using Roman numerals. I will use 3 for that, which is a line segment. And as a reminder, what a line segment is if I'm going from a point A to a point B, where my point A is, I'll denote this as R0, and I'll denote the point B as R1, as a vector of R1. If I think about this here, and I have R0, and I have R1, R0 and R1, and I want to come up with maybe a direction vector for my line going from R0 to R1, geometrically, this is actually R1 minus R0. And so what we can do then is we note that R of t is a line, right? The equations of a line is just R0 plus t times v. And so we could maybe write this as R0 plus t times R1 minus R0. Or more formally here, if I kind of move this around, you might get that I'm going to get 1 minus a t for R0 plus t times R1. And this is a parameterization for a line segment. You might ask yourself, well, what's my parameter domain? Well, the idea of the domain always, when I'm thinking about the parameter domain, is always, I want to plug in my initial point, and I want to get what value of t gives me my initial point. So for instance, here, if you notice, if I plug in, I want to get R0. So if you note, if I plug in t equal to 0, I'm going to get 1 minus 0 here. I'm going to get 0 here. So it's actually just going to be R0. So I start at 0. And then if you notice, if I plug in t equal to 1, this entire term goes away here. And I'm left over here with just R1. So this is my parameter domain for this guy. So always for a line segment, if you use this formula, you'll always go from 0 to 1. These are the 3 flavors. So you have a parameterization for a function that's explicit of one variable. You also maybe have a circle, which maybe is cosines and sines, which may be a little bit helpful. That usually is just dependent on the theta, right? And then the line segment also has this flavor here too. So those are the basic, those are the always really, those are the big three that we really are usually kind of parameterized for in this case too. So does that answer your question? Does anybody else have any questions, I guess, based off of that here? So yeah, so somebody asked, at least for the circle here, yeah, so in this case, if you notice, I can let x be equal to a cosine theta and y be equal to a sine of theta, because if you kind of do this out, right, I'm going to get a cosine of theta squared plus a sine of theta squared is equal to, well, it's going to be a squared times cosine squared of theta plus a squared sine squared of theta, and we get just a squared out of this, which is really nice. We get a squared out of this just by doing that. So we're able to write the x coordinates always as a cosine of theta and the y coordinates as a sine of theta. So that's why we're able to put it in like this. Because my goal here is not to express it in terms of, you know, r and theta. I'm trying to express something in terms of r and theta. But when I'm trying to parameterize something like this, my goal is to express all the x and y coordinates in some way that I can. And this is the way I kind of do it. Does anybody have any questions about that?
I do have a quick question. So
Sure.
the first way of finding equations, and then there's the third way with the line segments. Couldn't you do that both ways for a line segment in general? Like using the vector equation, and then, or just say you drew the graph and you found like the slope for one of the line segments, and then there's another one.
Yeah, so you could use this formula if you wanted to. Is that what you're trying to get at there? You're allowed to use that first one. Yeah, the only thing that you always want to make sure, if you want to create your vector, which is totally cool with doing, like if you want to just create your v and use that, that's absolutely okay. Most of the time then with your direction vector, if you do r1 minus r0, your domain will still be between 0 and 1. You always just want to make sure though, just to make sure that you maybe don't go too far. If you do exactly this, so if you make your direction vector r1 minus r0, your t will still be between 0 and 1.
Okay, that makes sense. Thank you.
Cool, no problem. Any other questions here? Okay, so I'm going to go on to a next topic. Does anybody want to, I guess, tackle another question here, either on the finals or just in general?
Could I ask a question about the Zengage 6.2 homework? I mean, 16.2 homework.
Sure. What question on that?
It was question 2. It's a it gives you two sets of points from 0, 0 to 4, 1, from 4, 1 to 5, 0, and the function is the integral of c of x plus 4y dx plus x squared dy.
Can you say the last, the one with dy really quickly?
X squared dy.
Oh. And you're saying that C is the line segment from 0, 0 to 4, 1, and
4, 1 to 5, 0.
4, 1 to 5, 0. Okay. So I guess we should tackle a couple things there then, here to kind of explain that. So the first thing I want to realize, I might go on a couple of different little mini tangents here before we kind of get into it. When I'm doing any of these types of problems, I kind of look at this and I want to at least know what this is actually physically representing. Right, this represents something of the form p dx plus q dy, kind of a curve like this. And again, what's important to note here is this is the same exact thing as a work integral, right? Where my vector field here is pq. These are the same exact kinds of equations, right? P dx plus q dy can be written as the same exact thing as the integral f dot dr. These are equivalent. And so this is a work integral. This is the amount of work it takes to move an object around a vector field over in my curve C here. Now, whenever we're doing this type of problem, at least in this one, if I kind of look at this, we always want to draw out your curve if you can. first off, if you could draw out your curve, it's always very, very helpful to do that. So in this problem, we are going from 0, 0 to 4, 1. I'm going to go with maybe like this. And then I'm going to 5, 0. So I'm going to here. And then I'm going here, like that. I'm going to call this C1, and I'm going to call this C2. Now, what's important to note here, I'm trying to look at something really quickly. QI, QX, no, it's not going to be that. Okay, so with this in mind, we want to first off try to figure out, okay, how do I start to evaluate this thing? Well, the first thing is to realize that if I have some function, if I have some integral like this, where I have a function of f of x, y, dx over a curve C, like this, how do I go actually about evaluating this? Well, the process is usually as follows if everything kind of in this way. So the first thing you do is we want to parameterize C. Parameterize C, as we kind of just talked about, as R of t may be between A and B. Then what I'm going to do here is I want to replace this. This entire integral can be replaced. I need to replace this dx. So as a reminder what dx is, if I have a dx or maybe dy, something like that, what I do to replace this, if I want to parameterize this with respect to t, I take the derivative of x of t. Or r of t here is x of t and y of t. And I replace this with x prime of t dt. If I had dy, I would do the same exact thing, y prime of t dt here. Okay? Something like that. Then what I'm going to do is I'm going to find f of x of t and y of t. I'm going to plug in my parameterization. Sometimes it's written as f of r of t. Something like that, where I'm going to plug in everywhere where I see x, I'm going to plug in x of t. Everywhere I see y, I'm going to plug in y of t. My goal there, and kind of my goal there, is I'm trying to find the function height at all of my points on the curve. So all the points on the curve can be described, I know, by r of t, and so I just plug in all the points there. And lastly, the final integral, I make these weird lines randomly, sorry. We note that I can rewrite this then as this. So dx can be rewritten as the integral from a to b of f of x of t and y of t. I plug in my function values and I multiply it by x prime of t dt. If this was dy, we would multiply this at the end of y prime of t dt there. Okay. Now this is if I'm trying to figure this exact equation out, you know, one thing I would always suggest doing, I know this is the 16.2 problem, but this is just good in general to check. Your vector field F here, your vector field F in this case is equal to x plus 4y and x squared. Now, we have these types of work integrals. We have a lot of different ways to evaluate these, as we'll probably do in this entire, in this review session. There's a lot of different ways. The first thing you always want to check, there's two things you always want to check, and we'll kind of go through them as we go through this, but first thing you want to check is my curve C closed? Do I start and end at the same point? In this case, it doesn't, right? I start and end at different points. So I can't really have any tricks there. The other thing I want to check out is this F is conservative. If F is conservative, right, what does that mean? That means, is there a potential function? Is there a function such that the gradient of that function is equal to my vector field? And the way we can always find that is we let this be P, as I kind of have, we let this be Q. And this is because of, by Clause's theorem, we need the mixed partial derivatives to be the same if there's going to be a potential function. So what we do is we see if there's Py is equal to Qx. We take the derivative of P with respect to Y, we take the derivative of Q with respect to X here. If I look at this very quickly though, I'm going to get that this is 4 and this is going to be 2x. And this does not equal each other. So F is not conservative. I'm sorry, I'm probably going a little bit on a tangent of your problem there, Owen there, but I think this is a really, really important point because whenever you look at this problem, this is kind of the exact process you want to do. That's something with dx and dy. You want to see if there's any tricks that you have up your sleeve. The first thing you check is my curve closed? In this case, it's not. Okay. I can't really use any tricks there. Maybe I could have used that Green's theorem, for instance, would be a curve closed kind of aspect there. The next thing you should check is maybe if your vector field is conservative. If it is, then we know that it's path independent, which means that I can take any path going from my starting point and my end point. Maybe that could simplify it by using, you know, the potential function, right? Using a fundamental theorem of line integrals, for instance. We can talk about that later. But this is at least the process you always want to think about when you're doing these problems. Because a lot of these problems, they don't tell you specifically what technique to use in this case. So in this case, we don't know. We know it's not conservative. We know it's not closed, the curve. So we have to do brute force method. And the brute force method here is kind of this exact process that I kind of described here. We must take this dx, exchange it for x prime. We must take this dy, exchange it for y prime, and then evaluate it from there. So the big thing that you want to realize here, especially in this problem, is I have two curves, C1 and C2. And these C1 and C2 can't be described with one curve specifically. So what I need to do is I need to realize, I need to calculate this. This is actually equal to the curve of C1 over the integral of the curve of C2. If I could use very loose notation really quickly here. So what I'm going to do is I'm going to do this exact process. I'm going to do the same exact thing for C1 and C2. But what I'm going to do is I'm going to do them individually, calculate the integrals, and add them up. Okay, so I'm going to do C1 here, just to kind of show you the process. And we can also include some of the cool questions that we actually just got asked before, which was about parameterization. So my first curve is from 0, 0 to 4, 1. It's a line segment. And so my line segment here, I'm going from 0, 0 to 4, 1. I'm going to do part, curve C1 here. I can go ahead and try to do that. And what I'm going to do is I'm going to create my parameterization as I kind of want to do here. So my parameterization, we know for a line segment, as we kind of just discussed, is t times r, 1 minus t times r0 plus t times r1. And we know this is going to be between 0 and 1. R0 here is just 0, 0. That's really nice. Plus t times r1, which is 4, 1. And I hope you'd agree this means that this entire thing goes away. And I'm actually just left with 4t, and t. 4t, and then t here. And this is my parameterization, where t is between 0 and 1. Okay. So now, that's my parameterization. That's first step. Second step here, I note that I'm going to have to compute x prime of t and y prime of t to exchange this for my time. Right? I want to evaluate this with respect to time. And to be able to do that, I need to compute x prime of t and y prime of t. This is x prime of t, this is x, and this is y. So I can compute x prime of t here is equal to just 4. And y prime of t here is just equal to 1. Also pretty nice, not too bad. And so what I'm going to do now is lastly here, I'm going to kind of combine everything into one integral here and kind of just evaluate this. So my curve with C1 now of x plus 4 times y times dx plus x squared dy is equal to the following. My integral now goes from 0 to 1. That's my parameterization. I'm going to replace x with 4t, replace y with t. Everywhere I see x, I plug this in 4t. Everywhere I see y, I plug in t. In this one, I'm going to get this as 4t plus 4 times t. We get 4 times t there, right? I multiply this by x prime, which is going to be 4 here. Then I add this to x squared, which in this case is just 4t squared. 4t squared. And this entire thing is going to be dt. And now I just evaluate this integral. 0 to 1. And I can go from there. This would be 32t plus 16t squared dt. I can continue evaluating that at that point. If anybody wants me to see that go forward, I'm at least stop there for right now. But then what I would do, once I've calculated this out, what I could do then is I could calculate C2 by doing the same exact process. So if I wanted to maybe use C2 just kind of as at least, you know, what we start off with here before I kind of end this, we're going from 4,1 to 5,0. And so again, I could use my parameterization as my line segment here would be 1 minus t times 4,1 plus t times 5,0. And using this here is a little bit more complicated. We would get in the first the x component, we would get 4 minus 4t plus 5t. Right, we would get that here, right? 4 minus 4t plus a 5t. And this y component is going to just have a 1 minus t. Or more specifically, 4 minus t, 1 minus t. Yeah. And so this again is from 0 to 1. I could again do the same exact thing, right? I would be able to do x prime of t here, which would be equal to -1. Y prime of t is equal to -1. And now what I would do is when I'm setting up this integral now, if I want to integrate this with respect to C2, right? Wherever I see x, I plug in 4 minus t. Wherever I see y, I plug in 1 minus t. And from there, I can evaluate this between 0 and 1. Afterwards, I can add up these two contributions. I can add up what this integral is and add up what this integral is. And that will give me the answer to this question.
I have a question. Could you go through how, like underneath C2, how you went from R of t, like how you went from that step to the next step?
This one here?
Like those like 2 or 3 steps, yeah.
So, right, I can, in this case, right, this could be written out as 4 times 1 minus t plus 5t and 0. Right, this is just me just moving in the 1 minus t into the 4 and the 1 there. And a t there moving in from the 5 and the 0. And then what I'm going to do is I'm going to take, oh, this is actually plus. I'm sorry, this is a plus here. My apologies. My bad. Because that's -4t plus 5t. So what I do then is I can then distribute this 4 through, and then I just add the x components together, right? So I get 4 minus 4t plus 5t. I would get that. And then the other component is just 1 minus t plus 0. And that's how I would get that one there. Does that make sense?
Yep.
Okay. Cool. Any other questions there? Owen, does that answer your question? I'm sorry that I went on a little bit of a tangent there, but I just wanted to kind of go off that.
No, that's perfect. Can I just ask one thing? So the R of t, that's basically just finding the parametric equations, correct?
Correct. That's finding the parametric equations. Yes.
Right.
Yeah. Parameterization is basically just finding the parametric equations for any curve.
All right.
Yep.
Thank you.
Yeah, no problem. Yes, it's always, if you use this formula for a line segment, it is always 0 to 1 for your parameterization. Use this exact equation. Okay. So, anybody has questions on this specifically? Any more on this problem that we just did here? Okay, I do have a question here that somebody just put in the comments on talking about the physical interpretations of curl, flux, and divergence kind of aspect there. So I'm just going to talk about flux integrals and then talk about curl and divergence briefly. We're going to talk about that. So let me go ahead and draw a line here so we can talk about that. Ooh. Move up a little bit more. I'll move up there. Okay. So I guess the first thing is if we have a vector field, let's assume we have a vector field here. F is equal to, I probably should move out a little bit more. Yeah. The vector field here is, I have to do this in 3 dimensions here, PQR. And there's a couple of really interesting things that you can calculate via a vector field. One thing you might ask yourself, and I guess the first thing that kind of gets asked here and is kind of to talk about the rotation of the field. The rotation, how does the vector field rotate? So basically, what am I asking? I'm asking if I place an object, if I place this bottle in a vector field, how will it rotate as I move? At what axis will it rotate on? And what we can do is we can calculate this via the curl. And the curl of the vector field actually tells you what axis the vector field rotates in. So the curl of a vector field, curl of F, which we sometimes denote as the cross product between the gradient kind of vector and in this field, we calculate it as the cross product. That's why we kind of write it like this, is I, J, and K. We then have in my second component, Y, Z. And in the third row, we have P, Q, and R. And calculating the determinant of this matrix, we can get the curl of the vector field. Now note the curl of the vector field, because it's a cross product here, is going to be a vector. The curl is also a vector field. The curl of F is itself a vector field. It is where it is basically all about rotation. So you can kind of imagine if I have an axis here, if I tell you the curl is in this direction, for instance, I place an object here, it's going to rotate in this way. It's going to rotate in that direction, about that axis. And we can calculate this out. And what we do is we basically, in the I component, we take the derivative of the R component with respect to Y. And then we take the derivative of Q with respect to Z, we subtract them. For the J component, we then take the derivative of P with respect to Z. We subtract that from the R derivative with respect to X. And lastly here, we then take QX and PY. Now, I want you to note something pretty interesting here. This probably shows up somewhere. You might think about that, right? Where is this showing up? Well, this actually shows up in Green's theorem. It shows up in Green's theorem. It also shows up in conservativity arguments for a two-dimensional vector field, right? If QX is equal to PY, if QX is equal to PY, we know that a vector field is conservative. But this is only for a two-dimensional vector field if I just have PQ. But if I have a three-dimensional vector field, how can I know if a vector field is conservative? And we've got to figure out is if a vector field is conservative in 3 dimensions is when the curl is equal to the 0 vector. So if the curl of F is equal to the 0 vector, specifically the 0 vector, it's not 0, the curl is itself a vector field. So it cannot be a scalar. So please make sure you write 0 with the arrow here, with that kind of the vector notation. This implies that F here is conservative. Which again, then you could use, for instance, fundamental theorem of line integrals, stuff like that. You could find out if I have a closed curve, right? I can maybe find out that this is 0. So the curl basically, if the curl is 0, this basically means that the field is irrotational. The field just does not rotate. If I place an object in it, it will just not rotate ever. It would actually just stay in the same direction. It will just move around in the same exact orientation that it started in. Here. If F is equal to PQR, F is conservative. Here, the vector field F here specifically is a conservative vector field. The curl of F is 0 in this case. That's what this means. The curl of F is 0. This is actually the gradient with F here. This is the curl of F is equal to the 0 vector. And then therefore, this implies that F is a conservative vector field. So with that in mind, we can then talk about one other thing that is a pretty big importance, which is called the divergence of F. We sometimes write this as div F, or sometimes write this as the dot product with the gradient field. And this is the divergence here. And we calculate this in some way. You can kind of think about this as the dot product between this vector here, the gradient vector, and then PQR. You can also calculate a two-dimensional divergence. Not really necessary for what we're doing. I can calculate something called circulation if you do it in 2 dimensions. But this kind of calculates PX plus QY plus RZ. And what's really important to note here is this is going to be a scalar value. Okay, it's going to be a scalar. And why is it really important to note that it's a scalar? Because a scalar value, a scalar function, integrates differently than a vector field. Right? A vector field, I have to kind of use a dot product kind of thing to get it, into some form, right, that I can maybe integrate it with. In this case, if I have a divergence here, this is going to be a scalar. It's going to be a number. It's going to be specifically a number. What does this actually represent? The divergence actually can be of three values, right? It can be positive, negative, or zero. And it kind of just talks about, you know, how divergent, I know this sounds really sad, but how divergent a vector field is from a specific point. So you can think about this. If the divergence of F is zero, what that means is more water. You can think about the vector field as water. That's always how I think about it. I'm kind of more of a fluids person. So that's at least how I go for it. So what happens is if my vector field divergence at a specific point is positive, that means more water is leaving rather than coming in. Okay, we call this actually a source. So more water is going in rather than coming out. You can kind of think about like a water gun, right? A water gun here, more water is leaving rather than coming in, unless it's a really, really rainy day. So that's kind of what this imagines it. So there's more water basically going out of this cylinder rather than coming in. If it's negative, that means more water is coming in rather than coming out. We call this a sink. Okay. And if it's a sink, right, that means more stuff is coming in rather than coming out. Lastly, if it's zero, that means an equal amount is going in and out. We actually call this incompressible. It's an incompressible fluid. If it's true for all, if it's zero for all values, we call this divergence free. We call this incompressible. And if its divergence is like that, you know, there's some. It's really, really nice. We can actually do a lot of really nice stuff with it. The divergence of F. Water, for instance, is an incompressible fluid. However, like ketchup isn't, and honey isn't. Air is sometimes incompressible, depends on that. But that's kind of at least the physical interpretation of what divergence really means there. And that's what's highly representative of maybe this idea of flux, right? And this integral specifically. Right, we have some integral like this, where we have f dot ds over my surface S. I'll move down, sorry. And f dot ds here, this is talking about the net flux of a net flux through an oriented surface S. And why do we have to say oriented surface? Because I have to talk about which way I'm thinking about going, right? Maybe I could think about, you know, if I have a piece of paper, am I thinking about how much fluid's going this way or how much fluid's going this way, right? In which direction? So I have to be very careful with that. And that's why we have to think about the normal vector and all that orientation-wise. So that's what's the oriented surface. This is basically, you know, what this really means. It basically is talking about how much fluid is moving through a surface basically in a unit time. Think about it that way. If it's positive, that means more fluids moving through it, more fluids moving, you know, through it than coming into it. And similarly, if it's negative, it means more fluids moving into it than moving away from it. That way. And I think that's basically, I know, I forget who asked that question specifically, but does that kind of make sense, Julia? Does that sound good, that process there, for those physical interpretations of curl, flux, or divergence? Does anybody have any questions about specifically that, or curl, or divergence, or flux there, at least the physical interpretations here? Okay. So yeah, so what do you use divergence for? Yeah, so somebody commented, what do you use divergence for? So divergence, you only really use it for the divergence theorem. At least for our interpretations here, we would only use that. What the divergence theorem says, and this is what's really important about the divergence theorem here, is here that we would get, if I want to try to calculate this integral, the flux integral here specifically, and I want to try to calculate how much fluid is basically moving through an object. If my S here is completely bounded, if I'm completely bounded here and I'm completely surrounding a surface, and I have a volume at a bounds. So it bounds a volume E, let's call it here. If I bound a volume E, what we kind of want to do is we can utilize the divergence theorem by switching this from a flux integral to a volume integral, by switching it through the divergence here. And so the divergence theorem says that I'm allowed to exchange this flux integral for just a regular triple integral where my integrand is actually the divergence of F. And this is going to be a function, right? If F is something, right? This is just transferring over some divergence of F here. And because of that, this is really the biggest point where you actually see the divergence happening, at least in the problems that we're dealing with here. And this really simplifies a lot of good things. So the only way you can use the divergence theorem, and this is really important, is when F is completely bounding an object. You can't use this any other time. You can't just use this when I just have just a regular piece of paper or something like that, or a plane. It has to bound completely. And it can simplify this greatly a lot of times here. Yeah. Does that make sense, Nikki? That sounds good. That's really the only place you really use divergence, at least in our problems that we've been using, at least at the moment. So Stokes and divergence theorem. So I guess a couple things that people are asking here. S is only bounded if I'm completely enclosing a surface, enclosing a volume. It would tell you. It would be interpreted within the problem saying that I'm completely bounding a surface. F specifically is not bounded. It's only the surface that's bounded specifically here. And it completely bounds an object. It will tell you that. It'll be very, very apparent in the problem that it will say like, oh, it's completely bounded here. The difference between Stokes theorem and divergence theorem, though, yes. The difference between Stokes and divergence theorem, though, are pretty important. Stokes theorem solves a completely different type of integral and solves a completely different problem, just in general. This computes the amount of flux moving through an object. Stokes theorem actually solves how much work it takes for me to move a curve around a curve. And specifically, this curve has to be closed. Right? So it's telling me here, it's kind of analogous to Green's theorem in this way. So it actually is not analogous. Stokes theorem is Green's theorem in 2 dimensions. They're the same exact thing, which is nice. So here, right, this will tell you if I want to have actually a closed curve, right, I would need to transfer this, if I want to use Stokes theorem, to the surface that is bounded by this curve or has the boundary of it. And you would use the curl of F dot ds. It actually switches to a flux integral, surprisingly, here, which is kind of nice. But regardless, I guess kind of the more important thing, this is a flux integral in the same exact way, but just with a different type of vector field. So that's kind of Stokes theorem. Yeah. So in this case, you're solving for a work integral. In this case, you're solving for a flux integral. Those are the big differences. Good question, though.
For that, could you technically use Stokes theorem and then use the divergence theorem? Because they're both like flux integrals.
Yes. So the thing is there, it is extremely rare to, and I actually cannot think of an example at the moment that this would happen where you are able to have a curve that is the boundary. Well, I guess the issue is, right, this needs to be a bounded surface. No bounded surface will have a curve because there's going to be no boundary to a surface that's closed, right? Because if I kind of consider a sphere, right, there's no curve that would be there. Like there's no boundary to this. The boundary is the entire surface itself. So the only way this could kind of happen would be a really, really rare circumstance that you have to do some really interesting math behind it. It would, at least for our purposes, that's probably never going to happen. But just as a reminder, this is always true for all vector fields. The divergence of the curl of F is equal to 0, always, for all vector fields. So if I take the curl and I take the divergence, this will always be 0 somehow, if I get that. So this is always true. The divergence of the curl of F is equal to 0. Yes, yes, yeah, you're absolutely right. So a bounded surface would be something like a closed object, like a full sphere that's closed, or you get like a paraboloid that includes both this bottom part and the top part, right? Something like that, yeah. Or a full cylinder, something like that. Does that make sense, Rachel, also? I mean, I know that was a kind of a weird way to get at it. That's very rare that you would actually get like Stokes theorem to divergence theorem here.
Yeah, that makes sense. Thank you.
Yeah, no problem. All very good questions everybody's asking. Any other questions, at least here specifically? I do have a question about going back to something like 12 and 13 and just talking about some things in the past that we might have, that might show up again on these exams. But at least kind of thinking about that. But does anybody have any questions about this here before I move onwards, I guess, from that? Okay, I will then really quickly, so the question was basically, you know, what might show up that was in the past on these finals? I think, you know, the practice finals actually do, I think, a pretty nice job of kind of explaining some big concepts that we've been dealing with. But the big thing, which is kind of crazy here, most of the stuff that we've done in the past shows up at chapter 16. That's what's bonkers about chapter 16. It's all of 12 and 15 like synthesized together. But a couple of things you might have forgotten about that you might want to remind yourself of. I actually do have that worksheet that kind of reminds you some things of that. You know, for instance, I would say make sure you know how to find the equation of a plane, equations of planes and planes and lines. You know, making sure you know how to compute the normal vector, right? So I made a worksheet. I was on Piazza. I posted on Piazza and I posted on my Canvas page at least, which was kind of like a fill in the blank kind of review of all 12 and 13 here. There's not a lot of stuff on there. You're absolutely right. There's not a lot of stuff on it because it's 50% everything prior to chapter 16 and 50% everything else, including like Lagrange multipliers. I mean, excluding Lagrange multipliers and all that, because that's also on it too. It's a little bit more heavily weighted there. But some things that you might have forgotten about, you know, maybe finding are lines parallel? Are they skew? Are they kind of stuff like that, right? Those are maybe some more important information you might have forgotten. You know, making sure you know the two definitions of dot product might be like an important thing, and noting that, you know, make sure you know what the cross product is, right? Cross product gives you a normal vector, but noting that this, right, the magnitude of A cross B gives you the area of a parallelogram made by two vectors B and A, for instance, you know, something like that. Give me this area, which actually shows up again when we think about the surface area integrals too. You might have forgotten maybe something about speed and velocity, acceleration and stuff like that, making sure you know how to compute that stuff. You know, recognizing surfaces. But we've been dealing a lot with them already, like cones and cylinders and you know, paraboloids. You're not going to be asked to have some weird stuff like hyperboloids. That won't be asked on it. But in this case, right, finding traces of objects, you know, being able to plot parameterization curves, plotting R of t, or knowing what R of t kind of looks like, using asymptotic behavior, using projections onto the XY plane and stuff like that. I mean, those are at least the things, at least that pop to my head really, really quickly here, at least in 12 and 13, that are just important stuff that you might have at least somewhat forgotten about. Knowing how to compute lines is always an important thing. Planes, we do that a lot too. So yeah. I mean, chapter 16 thankfully covers a lot of that stuff. That's also why chapter 16 is so difficult, unfortunately. Yeah, no problem. Okay, that's kind of that. Anybody have any other questions they want to ask? Anything they want to go for? Feel free.
When we're doing surface integration, there are two similar equations. It's like R sub U cross product with R sub V, and it's a magnitude. But then there's also when it deals with it's you take the cross product, but then use dot product with the vector field.
Yes.
When do you know, or how do you know which version to use?
So the big thing, I guess, is what each interpretation, I guess the interpretation of that. If I want to find the surface area of a surface S, what I do is I actually calculate this, right? I can parameterize this as R of UV, where maybe UV is in some domain D. And then my area of this surface, the surface area specifically, is with the magnitude there. RU cross RV dA. Actually harkening back a little bit that we actually just talked about here, like the magnitude of A cross B gives me the area of a parallelogram. And this gives me another area of a parallelogram. It's just adding all the little parallelograms in the entire surface. So if you're asked to solve for the surface area of something, all you do is you compute RU cross RV of the magnitude, and you get this kind of vector. You get this equation. If I'm asked for the flux of flux through F of a vector field, let's call it F here. This flux here is actually calculated as this guy right here, which we can parameterize and then calculate it as F of R of UV. But then kind of realizing here, this is going to be a scalar value, right? The norm of something is going to be the scalar value. It's going to be something we can integrate already. Here we have a vector field. So I can't multiply it by a magnitude, right? A vector field, I would have to take a dot product in some way because I need to get it kind of unraveled, if that makes sense. I need to get it kind of in integration form. So what I could do is I could do RU cross RV here, which is my normal vector. And then I could calculate this as dA. That's the main difference between the two. One is calculating specifically the area. You use this as well, kind of if you see some integral like this, where I have over a surface. If I have just a function like this guy, it's very, very similar to the way we do integrals back with just f of xy over a curve. Right? We again parameterize and we compute f of r of uv, but in this case this is already a scalar function, so I can't take a vector, right? I have to take the magnitude of the vector that kind of transforms it, because I need to be able to multiply it. And those are basically the three differences. So this right here could be thought of almost as the density of that sheet, where the density, this entire thing would be the mass of my sheet S here, my surface S, where F here could be thought of as like a density. And so if I have something like this, I have to use the magnitude of RU cross RV, because I literally can't take a vector. It wouldn't make sense to have a vector multiplied by a number. I have to integrate. I mean, it does make sense, but I have to integrate a scalar function to get around that. And so that's why over here I need to do RU cross RV, because I need to take a dot product. I need to take literally a dot product to get to a scalar form, so I'm able to do that. Does that make sense?
That actually makes a lot more sense now. Thank you.
Great. I'm happy. I'm happy it does. Good. Flux of S, the flux through my surface field. This kind of means here, right? Through my vector field. I kind of simplified this. Sorry. A vector field F here. So I'm basically just taking the flux. So flux basically means how much fluid is moving through my surface F. And my vector field, my vector field is the thing that I'm moving through my surface S in that case. So that's what that kind of is implying there. Okay, any other questions there? Yes, I apologize. I do have, my handwriting is not the best. My mom tells me that all the time. So I'm quite aware. I'm sorry about that. I'm actually debating about going and getting like one first grade book to go ahead and try to figure out how to write again. I'm sorry about that. Okay, Any other questions that I could answer? Any problems? I have all the finals up here too, so if you want me to do a problem or something like that, I feel free to, I can go ahead and do one of those. Or I can just talk about a concept, whatever you want me to talk about.
If no one has any questions, I would just say chapter 16 in general, because that's what we've got like the most on the exam for.
Sure. Do you have anything specifically in chapter 16 that you want to do?
Not particularly.
We do one of the problems on the exams that have to deal with Green's theorem. Orientation is usually the problem whenever I try to do it, and I always have a hard time.
Sure. So do you have a question that's Green's theorem in mind? Let me see if I can find one. So,
I mean, I know in some of the exams that it does provide like saying that it's positively oriented, but I don't know if there's something that they give us actually where we have to make sure that it's already positive or not.
Yeah, so when you use Green's theorem, you can always use Green's theorem if it's closed. You just might have to put a negative sign out in front or something like that when you're using it. Let me see if I can find a Green's theorem question that would kind of hit my point home here. Because why is every single I can't find a Green's theorem one. Oh yeah, let's try this. So in this problem this is spring 17. And then after this, well, yeah, I think it might be beneficial. I think somebody was asking to do like Lagrange multiplier stuff. We can definitely talk about that. So spring 17, question 10 here. It talks about this. So it's the Green's theorem, which actually tells me Green's theorem. Cosine, e cosine of x, e to the cosine of x, dx plus xy dy here. And I have my curve is a positively oriented curve. That's nice. The positively oriented, which starts at 0, 0, goes to 1, 1 on the line x squared, and then goes back to 0, 0 on the line y squared, x equals y squared. Okay, so this again, and I would like to, if you don't mind, I would like to at least talk about here. I think one of the hardest things on chapter 16. This is something I've TA'd this now for my 5th semester, I think, doing this. Yeah. I've noticed all the time, and this is a question that a lot of students come up with, and it's a really, really important question. It's, if I see a problem, how do I know what technique to use? We see so many techniques in chapter 16. We see all these different techniques. How do we come up with this big idea? What technique do we use to solve this type of integral? In this case, it's again a type of a work integral. Right? We again have something that looks like the integral of c p dx plus q dy, which again can be thought of as f dot dr. And the big thing we always ask are two questions whenever we're trying to come up with this integral, to try to figure out what technique we want to use. The first thing, and we can actually make a little bit of a Punnett Square. And I kind of did reference this in a video. And I'm not sure if your other professors or anything has kind of referenced this, but I find this is a really clean way to kind of come up with what the techniques to use here. Always two questions to come up with. Is your vector field conservative, and is your curve closed? Is F conservative, or is C closed? And we have yes, no, yes, and no. Okay. These are the two questions we always ask with these type of questions. And this will give us the exact trajectory of a problem that we need for a work integral. This is specifically for a work integral, something that looks like p dx plus q dy, or the integral of f dot dr. If f is conservative and my curve is closed, I automatically know that the amount of work it takes to move an object like that has to be 0. So your answer is automatically 0, period, done, which is really nice. So if your vector field is conservative and your curve is closed, your answer is 0 always. Now, if my vector field is conservative and it's not closed, Well, the technique I do have then in my arsenal, right, is the fundamental theorem of line integrals, because I know that I can then make this path independent, and I can just solve the using the potential function, right? I can use the fundamental theorem of line integrals, and I could solve this as like phi b minus phi a, kind of like subtract the potential function at the end point, subtract it from the beginning point. That's that technique. If f is conservative, if it's not conservative, but my vector field, but my curve is closed specifically, I can then use Green's theorem. Or if I'm in 3 dimensions, that's Stokes theorem. Okay, that's that way too. Same idea. Green's theorem is just a 2-dimensional version of Stokes. And lastly, if it's no and no, if I'm not conservative and I'm not closed, I have no other techniques other than just go brute force method. And by the brute force method, what do I mean? I mean what we could have did back in that other problem where what we do is parameterize the curve, find r prime, take the dot product, or maybe just take x prime of t, y prime of t, however we want to think about it. So, excuse me. So because of that, this is always what you want to do when you see these problems. Because I have seen, and I honestly don't know what they're going to do. I will not see the final until the exact time that you do. So if you've seen on this last couple of, on these finals that they give out, some professors or sometimes they give you the exact technique you need to use, right? They go, use Green's theorem, use fundamental theorem of line integrals. However, sometimes they don't. And they just kind of make you just come up with the process yourself. I really don't know what techniques they'll use here, but this is kind of the exact idea. So this is the process you always want to use. Now in this problem, the first thing we notice is I have this curve here. I have this curve, which is xy. So I'm going from 0, 0. I go then to 1, 1 on the line y equals x squared, something like this. And then I come along and I go back down this way on y equals x squared. Okay, so I have this curve C. I'm told it's positively oriented. Positively oriented in 2 dimensions basically just means counterclockwise. So I'm moving counterclockwise, it's positively oriented. Now, I have a closed curve. So I have a closed curve. This is great. Now, if I have a closed curve, I can then utilize either knowing that it's 0, or if it's Green's theorem here. And yeah, so to check if it's conservative or not, right, what we do is we go ahead and do py equals qx, exactly that. We can see that it's a closed curve because we start and end at the same exact point. So we always kind of know that. So to check if it's conservative, we then now go ahead and compute py is equal to qx. And what's kind of nice too is to realize that this shows up very, very much so in Green's theorem specifically, because we have to do qx minus py. So if we see this, we can actually compute py. Py here, I hope you note there's no y's here at all. Right, this is p, so this is 0. That's nice. Qx here, well qx, this is just equal to y here. So py does not equal qx, and so therefore f is not conservative. Not conservative. Okay, so if f is not conservative and we have a closed curve, we can utilize Green's theorem here. And yeah, so they'll usually give you the point almost all the time. If not, they'll just say, oh, it's the intersection between these 2 things, and it's the curve of intersection between these 2 curves or something like that, or something along the lines of there. The point should not be too bad when to infer in a problem like that. So again, Green's theorem, what does Green's theorem say? Let's just kind of remind ourselves. Green's theorem says if I have a positively oriented curve, which means that I'm going counterclockwise, what this says is I can compute this as a double integral over my domain D now that I'm being bounded by, where this domain D is actually this guy. Here, I'll kind of erase this right here. That's my domain D. And this becomes qx minus py dA. And now realize here really quickly, and this is something I really wanted to say, if this is conservative, I hope you'd agree this would imply that qx would equal py, and therefore you get 0, which gives you this kind of condition here. this is one way you could definitely check to see if my vector field, I mean, this is one way you could just check that, a conservative closed combination there gives you 0. In this case, right, we can then come up with my domain D. I can utilize this because I'm positively oriented. If it's negatively oriented, we put a minus sign out front. That's all you do. That's the only difference that you do here. Put a minus sign out front. So Qx here is y minus 0, because that's py, dA. And so therefore, it is just equal to the double integral of the function of y over this domain, which is in a problem that is a lot simpler to solve. Because think about the process that you would have to go through if we did not have this. You have to parameterize your curve C, which in this case would require you to do 2 different integrals. You would then need to plug in R of t into here, which if I were you, I don't want to even touch e to the cosine of x. That seems disgusting and completely meaningless, and I don't want to really care about that. So a lot of times, that's kind of a dead giveaway that you should be doing something a little bit more like a trick, either using Green's theorem or fundamental theorem of line integrals. If you have something really, really complicated here, there's got to be some trick that you can use, because there's no way they're making you go through that whole process. It's a 2-hour exam. There's no way they would do that. So what we do here is we just now come up with the limits of integration for this problem. The limits of integration for this problem, then we can see here, we can either write this in terms of an x or of a type 1 or a type 2 integral. I kind of think about it, at least in this case, I can write this maybe a little bit easier as with integrating with respect to y first, kind of going up in this direction here. We always enter here. We always enter from this bottom part here, which is the curve of y equals x squared. So we always are going to be below by x squared. And we're above by the y squared equals x curve. I do have to solve this out for x, because I would for y, because I need to use this, equals y equals plus or minus the square root of x. But we also note that this is just the positive branch. So this top part would just be the square root of x here. And then my domain would then be between 0 and 1, because my lowest x value is 0 and my highest x value is 1. So then what I could do is I could take this guy right here and plug this back into here and then solve out this integration. And I think I will stop there unless somebody actually wants to see this go out.
I have a question about the bounds.
Yeah.
I just forget, how do you determine that like the y bounds are going to be the functions being solved and the x is going to be the constant bounds? I forget how to.
It's honestly up to you. It just seems like what's the easiest here. There's not really a right way. In this case, I know here first off that polar coordinates probably would never work. It'd be kind of bad to do. So what I could do is that I could integrate with respect to y first, or I could do it with respect to x. In this case, I need to have a clear entry and exit for me to come up with my bounds. In this case, I have a clear entrance if I move in my y direction, right? And I have a clear exit always. If I move in the x direction, I also do have a clear entrance and exit too. I'm always entering from this curve. I'm always exiting from that curve. So it really doesn't matter, at least in this part, because this curve can be written as a type 1 or type 2, which means I can integrate with respect to x first and then y, or with y and then x here. There can be some different types of curves where it will greatly benefit you for integrating one of them instead of the other way. Is that kind of what you're getting at?
Yeah, so we could choose, but we choose to do x as the constant. Are you? Okay, never mind. I think I see.
Yeah, so always, whenever I figure out which one I'm integrating with respect to first, the next one must be a constant, right? That's always what's going to happen when I integrate that. Yeah. So yeah, and I'm going to stop there at least for right now, because this integration is just, that's not too bad to kind of do. But just make sure you know how to integrate that stuff. Unless anybody wants me to see it, I'll be happy to kind of do it. Okay. Does that answer your question about Green's theorem? I forget who asked that question. I'm sorry.
So that answered my question.
What was that?
You did answer my question.
Okay, cool. So yeah, I kind of maybe went a little bit too long in that, but I think this is at least important to kind of go over this whole process here. This kind of choose your own adventure board. Yeah. So yeah. Does anybody have any questions about this at least at this point? This kind of stuff. Any of these techniques you want me to talk about here? I know the only thing we really didn't talk about is the fundamental theorem of line integrals on this one here. Yeah. So I think well, that's the only one we haven't talked about. If anybody wants me to discuss that, I can. We could do a problem where we find a potential function and stuff like that. If you'd like, up to you guys though. If you guys have other things you want me to talk about, I'd be happy to do that instead.
I say let's do it.
Let's do it. Okay. Let's just complete the full. Let's complete the full Punnett Square. So let me see if I can come up with one. Is there a problem here that we can do with that? Yeah, let's do that guy. This seems fun. So this is problem 5 from spring 2018. Problem 5 from spring 2018 is this problem. So we have F here, which is done by an overkill. I don't know why they put the bold and the arrow, but that's a bold choice. And a vector field of e to the y, x e to the y plus 2y here. Okay, so there's this whole part where they kind of go through, they actually take A, B, C, and D. They actually go out and step it out, which is good. But I want you to just kind of realize here, if they ask this question just off the bat, right? If they ask this question off the bat where curve C is this portion of the ellipse, x squared over 4 plus y squared over 9 equals 1, from 2, 0 to 0, 3 in the first quadrant. That's what this problem is. So I'm basically trying to find, I have this vector field F. I want to find out how much work it takes to move an object around this vector field, around this curve C, where this curve C is denoted by this. So it's some curve like, I'm starting at 2, 0, which is here, and then going from 0, 3. So it's something like that, in that direction there. Okay, so this is my curve C here. And again, let's understand both parts here. First part, like if I don't know what technique to use at all, right? If I don't know what technique to use, I could then say to myself, okay, well, all right, I need to see two things. Is my curve closed? No, curve's not closed here. Not closed. Okay, that's sad. That really that would simplify a lot of things, but it's okay. Let's just hope it's conservative. If not, this is going to be kind of a tough parameterization. So to see if F is conservative, is F equal to a potential function? Does this exist? So this is P and this is Q. We take Py and Qx. And again, this is because, right, we have to do this mainly because of, yeah, so we have here, because we want to go, in this case, right, we want to make Clause's theorem work. So yeah, this curve is just x squared over 4 plus y squared over 9 equals 1. Equals 1 between the point 2, 0 and 0, 3 here. So to see if this is conservative, we need to see if Py is equal to Qx. Py, if I do this, is just equal to e to the y. Qx here is this 2y will go away, and I'm left with just x e to the y. Well, x e to the y, the derivative of that is just e to the y, because x is a polynomial. It's e to the y. And so therefore, we get that Py is equal to Qx. And so therefore, it's conservative. And again, what does it mean to be conservative here? Conservative vector field means that there is a potential function such that F here is equal to the gradient of that potential function. And now my goal is to solve that potential function. Because what I'm going to do then is use the fundamental theorem of line integrals, which says that the integral of f dot dr of a conservative vector field, I can write this maybe as this kind of idea now. This is now equal to just the value of the potential function at my end point. I write this as the end point, kind of the end. If I parameterize my curve C, R of B is like the end point. I can even write phi at end point if I wanted to, and minus phi at start if I want to be extremely, I think that might take away my by degree by writing this, but just agree with me here. Phi of n minus phi of star, right? We kind of just do it that way. So let's try to find this potential function here. So there's a couple of different techniques to do it. There's actually usually two techniques that I show. I'll show both of them because I've actually had students like both ways preference. I personally like one way. It might be a little bit longer, but it kind of, I think, takes the guessing out of the way, out of the picture here. But it's up to you guys. I'll show both. They're not too long to kind of explain, so I'll do that. So if I assume then that f is equal to some potential function, this means that this is phi x and then phi y. And this equals specifically e to the y, and then x e to the y plus 2y. So this implies then that the x coordinates have to be the same and the y coordinates have to be the same. So this means that phi sub x is equal to e to the y, and phi sub y is equal to x e to the y plus 2y. And now my goal is to try to come up with my potential function such that the derivative with respect to x is this, derivative with respect to y is that. So you can take either one at the moment and integrate it, because we need to get back up to my original potential function. So I'm at a derivative, I want to integrate. This guy right here, what you can do is we can integrate this with respect to x. If I integrate this with respect to x, kind of do this dx here, this would just become x e to the y, because this is a constant, so I just gain a polynomial of x. This become x e to the y. But when I integrate with respect to x, what do I have to add? Well, usually when I integrate, I have to add a constant of integration. But in general, what I have to do is I have to remember that if I take derivatives with respect to x, and if I just have a function of y, that will go away. So I have a constant of integration, I have a function of integration, which is in terms of y. So there's this mystery, I will call this g of y here. If I can write the letter g, wow, Nick, that was horrible the first time. 5 times you wrote that, geez. There's a function of g of y here. And so I want to find this function g of y. There are two techniques in order to do that. The first technique is as follows. The first technique you can utilize is just by integrating phi sub y back up to y. So doing that, we then integrate phi sub y with respect to y, and we would integrate x e to the y plus 2y dy, something like this. And we would integrate this, and we get phi of xy again, which is equal to, well, integrating this with respect to y, this will just be x e to the y, right? Nothing else gets added. This right here will be y squared. And when I integrate with respect to y, I always have to add now a function of x, which we call h of x. And what I note now is that this function and this function must be the same. I've integrated back up to my original potential function. They must be the exact same function. So because of that, I can kind of play like a piecemeal game and kind of figure out what the missing g of y or what the missing h of x are. In this case, I see here that, okay, well, this missing g of y must be y squared, because they share this x e to the y term. And this missing h of x term doesn't really exist. This is really 0. Okay, so you have a g of y here that's really going to be y squared. So your full potential function then is equal to phi of xy is equal to x e to the y plus y squared plus some constant k. We usually just let this k be 0, which is okay to kind of leave it like that. If it asks to find a potential function, you only have to find one. So you can just let that be 0. Usually. That's one technique. The other technique is a little bit more procedural, which is okay. I think it's actually a little bit better, but it's maybe a little bit longer and a little bit more tedious. Up to you though. So what I'm going to do now is I'm up to this point right here, and I want to basically find this g of y. I want to search for this g of y. In order to do that, well, I know I have this other piece of information, which is that the derivative of this function must be equal to this. So what I could do is I could take the derivative of my now incomplete potential function here. If I do this here, I would get x e to the y plus the derivative of g prime, just g prime. Sorry, plus g prime of y. And now I know that this function and this function must be the same. And if you note here then, well, if this function must be the same, I must have that g prime of y is actually equal to 2y. Because these two things would cancel each other out. And so I'm left with g prime of y is equal to 2y here, which we can then integrate. It would get g of y is equal to y squared. And then we would get the same exact thing, because we would get that c of xy is equal to x e to the y plus y squared. Something like that. So there's two techniques there. Whichever one you like to do is better. I think DJ usually uses this technique down here. I actually like this technique too, because it's kind of more procedural and it's more exact rather than kind of a guessing game. But it's honestly your preference. So now I have this potential function, and I now want to compute. Well, in just as kind of as an example, part B kind of says to integrate this flux integral where C is just a counterclockwise circle of radius 3 centered at some point. If it's a closed circle, right, we know it's a 0. If it's a closed curve, this is going to be 0 because F is conservative. We get that. In this part D here, we're asked to, where C is a portion of the ellipse x squared over 4 plus y squared over 9 from 2, 0 to 3, 0, 3. And so we're starting here and we're ending here. So in order to now use my fundamental theorem of line integrals, if I want to compute this guy, I can now utilize the fundamental theorem of line integrals, which says, okay, I am now trying to evaluate this potential function at the end point, and I'm subtracting it from the start point. My end point here is this guy right here, which is going to be 0, 3. I subtract this from my potential function at my starting point, which is 2, 0. And now I literally plug it into here. I don't plug it into the gradient. I don't plug it into my vector field. This is what's really important. This is something I've seen a lot when grading these exams. A lot of students, what they'll do is they'll go here and they'll go, oh, I'm going to plug it into this vector field. No, you plug it in to literally the function. It should be a number, not a vector as your answer. So because of that, I plug this in. I would get, 0 e to the 3 plus 3 squared minus 2 e to the 0 plus 0 squared. So that kind of gives you here, right? Just plugging it into here. This is just 0. This becomes a 9. This whole thing becomes a 2. So this all just simplifies to 9 minus 2, which is 7. That's your answer. So because it's conservative, right, it's path independent. All that matters is where I start and where I end. And that's what this kind of says here. I calculated the potential function out. Yeah, so those are the three types of techniques you really have to solve this type of integral here. And using this. Does anybody have any questions about this technique specifically? I hope these two techniques kind of make sense here. It's honestly up to you, whichever point you want to kind of do that. Any other questions here? Okay, so I could talk about 14.7 and 14.8. Yeah, so what about 14.7 and 14.8? Do you want to talk about that? I guess about mins and maxes, about Lagrange multipliers. We could do kind of all that. I think, let me actually see. So I just want to talk about at least, oh no, where am I? I have lost, oh no, I'm here, gosh. This is an infinite whiteboard. I'm not very good at this. I should be using this more. So I want to at least discuss here 14.7 and 14.8 just pretty briefly on how do we go about doing these types of problems? I'm finding minimums or maximums, classifying points. So the first thing that you should always check out here, let me see if there's actually a problem you might be able to do kind of as an example with it. Let me see. So, we can just talk about this. So if I have a function f of x, y, this is two variables. I want to find minimums and maximums to it, or if I want to find critical points. As a reminder, what is a critical point? A critical point, if I had just f of x here, right? We usually say that a critical point is when the derivative f prime of x here, f prime of x is equal to 0. Something like that. And from there, we found a critical point, right? Because our tangent line is horizontal. Well, then we used to classify it. We used the second derivative test, where what I did is I had either it was greater than 0, which means it was concave up. Right? It was concave up like that. So therefore, this was a min. If it was down, kind of like that, it was a max, because it was concave down. And if it was 0, it was inconclusive. Right? We didn't really know what it was. It was kind of this weird kind of part there. So now, if I have a function of 2 variables, how do I start to think about that? Well, I need 2 conditions to hold to find all the points that are critical points here, to find all the points that are, you know, kind of flat or possible maxes and mins. So to realize here, what we need to do is we need to find all the points such that fx is equal to 0, the derivative with respect to x is 0, and the derivative with respect to y is equal to 0. We need both of these things to hold. And we need to find, usually it's just solving systems of equations to be able to find, which is what technique is what here. So for instance, you have, let's say we have this function, which is x squared plus 2y to the 4th plus 2xy, for instance. And I wanted to find all the critical points here. Excuse me, I'm just going to blow my nose. Sorry about that. It's really bad because I'm starting to have allergies, and I told my class this. I took this allergy medication, and I had to go to the urgent care because I was allergic to it. So I did not know that. I've never been allergic to anything in my life really, other than one medication, and this is nothing even remotely close to that. So I'm kind of somewhat dying at the fact that I don't have allergy medication, but I'd rather not die with eating my allergic one. So in order to do this, right, what we do is we find all the points such that this first derivatives are equal to 0. And so what we do is we take f sub x and we take f sub y. Take this derivative with respect to x here. We get 2x plus this guy over here would be 2y. Right, that would be 2y. F sub y here, which would be here, this would be 8y to the 3rd plus 2x, if I'm not mistaken. Yeah, something like that. And we set these equal to 0 now. We're just trying to solve for all these points that kind of do this. Now, this might be a little bit more of a complicated one that you might see because it's just a lot of things, but this is something at least you want to at least try to do. So the technique that you might use this is we see in this first part that, okay, well, this would actually be 2x plus 2y is equal to 0, which means I would get like y is equal to negative x. Right? If I move this over, I would get that y has to be equal to negative x here. Yes, the prerequisite, yes. This is actually a really good question that Jang just asked there. All of these problems, and this is something that's really, really, really a sinister thing that they do with these true-false questions on here. They will give you points that are not critical points and that will satisfy the saddle point or minimum or maximum or all those things. So you must check that all these things are critical points always. It's really, really kind of a weird way that they really make sure that you check 2 things. One is a critical point, 2 that it satisfies that matrix thing that we'll talk about in a little bit. So we get that y is equal to negative x here. And then what we could do is we could plug in, yeah, you could use, but I mean, I think somebody just asked if in this kind of example, you actually can just plug in any points here to see if they satisfy it. For instance, this first part is xy equal to 0, 0 a critical point? It is, because if I plug in 0, 0 and 0, 0 here, then we would just get that this equals 0 both times. That's at least the opinion, but you should always check that it's a critical point. You can always just go ahead and check in x and y, whatever x and y you want, to see if this satisfies a critical point. You don't have to go through the whole process to find all of them. But this is at least how you would do it if you were going about that process. So now what I could do is I could substitute in my y is equal to negative x. Actually, I'm actually gonna change this because I see that's probably a little easier for me. X is equal to negative y. So I'm gonna plug in x is equal to negative y into here. We'll get 8y to the third minus 2y is equal to 0. And what we could do is we could factor out a 2 here, a 2y, and we would get 4y squared minus 1 is equal to 0. And so from this point, we can actually find that we can get two numbers that are possibly a couple of options for y. Right? We can get that y is equal to 0 is a possibility. We could also get the other possibility of 4y squared minus 1 is equal to 0. So something like this, we can get y squared. We get y squared is equal to 1/4. And we can then satisfy this as y is equal to plus or minus 1/2. Okay, so I found here that y equals 0 or y equals plus or minus 1/2 are possible critical points. And so what I could do then is I could plug in back into here to get my x values. So this one implies that x would be 0. And so I have a point 0, 0 based off that. Here we note that these two will give me 2 more points by plugging in 1/2 to here. I would get negative 1/2. So I would get negative 1/2, 1/2, and 1/2, negative 1/2. And these 3 points are the only critical points that we have. Okay, those are the only 3 points that are critical points. They've satisfied both at the tangent line, both in the x and the y directions, or have a slope of 0. So that's how you find critical points, just in general. Now, how do we classify them? Well, what we do is we have some form like a second derivative test, but again, we kind of want to think about that. We have so many different second derivatives in 2 dimensions, right? I have xx, xy, yx, and xy and yy, right? So I have this guy, I have this guy, I have this guy, and I have this guy here. And what we do is we kind of take a combination of them. We actually take the determinant of this matrix. This matrix is actually called a Hessian, for those of you who are actually wondering. And what we can do is we can calculate this out. And it kind of also sometimes looks like fxx times fyy minus fyx times fxy. It looks like that. We can actually simplify this down because by Clause's theorem, if this all holds, these two have to be the same. So we get fxx times fyy minus fxy squared. Now, I would never memorize this. I would highly suggest you don't do that. I would just put it into this determinant every single time. But this is actually a really nice form to think about what does each one really mean, right? What does it mean when this is positive, when this is negative, or when this is 0? And we kind of have to classify that. So there's 3 options. This determinant can be negative, this can be positive, and I'm writing that completely directly opposite of what I'm saying it, but it's positive, negative, or 0. Now, I want you to kind of realize something here. And if this determinant is positive, would you agree then, and this is something I want you to think about, would you agree that this implies that this coefficient here, this fxx times fyy must be positive? It must be positive because this is going to be a negative value. So this value has to be a positive number to even have a chance at this being positive, right? This has to be a positive number. So if this is a positive number, that means then we have 2 options. Either these both things are positive or they're both negative. So if it's positive, we have a kind of a bifurcation here. We have 2 options. One, that fxx is positive or fxx is negative. We only have to check one of them because we know that they have to be of the same exact sign. You could check fyy if you want. But just as a reminder, you could just check whichever one you want. You only have to check one because they have to be of the same sign. If fxx is positive, that means that in the x direction, the concavity is facing upward. And that also means that the concavity of the y is facing upwards too. So that would mean we have kind of like a bottom of a bowl, which means that this is going to be a local minimum. Okay. Similarly here, if I have an fxx being positive, it's going to be a concave down and concave down again. So we're going to get something like, you know, a paraboloid on the top there. So we're going to kind of like a local max. Okay. Now, if I have this as a negative now, well, one of the options, I hope you'd agree, for this being negative, just gotta bear with me here. If this is negative, this would mean that a possibility could be that this entire term would be negative, right? That would automatically imply it. And that would mean that fxx and fyy are of different concavities. So that means I would have something like this, and I would have something like this. So you gotta think like a saddle, right? I have concavity going down this way, I have a concavity going upwards like this. And so because of that, we call this a saddle point. As I think it was Mickey that put that in the chat. Yeah, kind of like that there. The saddle point. Saddle points are weird. But if it's negative, we automatically go saddle point. There's no necessary for us to check any other conditions. And if it's 0, again, this is inconclusive here. We can't really do anything about it. We have to kind of use other techniques. Other techniques are much more complicated than anything we'll do here. Some of the other techniques you might use, just in general, could be numerically visualizing it. That's usually something you would try to do. Or maybe try to calculate what's happening around it. That usually gives some insight as to what's happening. So for instance, I'm only going to do 1 or 2 of these because this takes a little bit of time to do all of these here. But what we can do is we can then calculate and to figure out what all these look like. Right? What we would have to do is we would calculate all these different derivatives. So we would calculate fxx, fxx, fxy, fyx, and fyy. So fxx here is just going to be actually 2. fxy is going to also be 2. Right? I know that. fyx is actually also just 2. And fyy is going to be 24y to the square. Y squared, just like that. Now, what we do is there's 2 ways you can kind of go about it. I'm more of the camp of you can just go ahead and compute this determinant just in general. It's okay to do that with all the y's in there too. I usually suggest to compute the determinant for each individual one. So what do I mean by that? To take 0, 0 here, we would get that fxx is equal to 2, fyy is equal to 2, fxy is equal to 2, fyx is equal to 2, and fyy here, just plugging in 0 would be 0. And that would do that. So that would mean then that the determinant here would be equal to 2, 2, 2, and 0, which would then imply this is going to actually just be -4, which is negative. And so therefore, we know that since it's negative, this means that 0, 0 is a saddle point. Yeah, like that. Similarly, we could do, I'll do one more, just got to show you it. 1/2 and -1/2. If I do that one, I again get all the same fxx and fyy and fxy and fyx, but fyy will then just be here 24 times -1/2 squared, which is going to be equal to 6, 24 over 4. And so my determinant is going to be 2, 2, 2, 6, which is going to be 12 minus 4, which is equal to 8. This is a positive number. So if it's a positive number, we then note that fxx here, we just take one of them, which is fxx, for instance, in this case, is greater than 0. And so therefore, because we have fxx greater than 0, and our determinant here is greater than 0, this will give me a local min. Let's get to the process here. Yeah, so that's actually the process of at least trying to come up with critical points and kind of classifying them. That's really the basics of it all.
I have a question about what you just did. So if you found that d was greater than 0, and then fxx, unless it's equal to 0, you're going to have either a local max or local min.
Yes.
Okay, and if you do, if fxx was equal to 0, what would that mean?
Well, if fxx is equal to 0, you actually can't have this be positive because this entire thing would be this entire thing would be 0, right? Yeah.
Okay. Thank you.
Yeah. No problem. Any other questions there? Okay. So that's at least that. Does anybody have any other questions when we talked about them? So this is max and mins here. I could also go through the Lagrange multipliers. I just want to know if anybody else have any other questions before we get to that about other than Lagrange multipliers. Does anybody have any other questions that you want me to talk about just in general?
Do you think they would give us a question that asks for like the absolute max and mins? Because I know Professor Salmon said that takes a while. So I was just
That does take a while. That really does take a while. I have genuinely never seen it on an exam. I don't think that's something that you would see, but you know, the absolute max and absolute min. I mean, I guess the thing is, you know, something like this here, I could say like an absolute max and absolute min on a domain, but they would have to give you something really easy because that's a really long problem. It's a really long problem because that's both doing this process on top of using Lagrange multipliers, right? So it's a double process. It's a double whammy. So if they're going to do that, that has to be the only question they do about that problem, about that stuff, which I don't think they really would. But again, I'm always scared to speculate. Yeah, I think absolute max and absolute mins are kind of more difficult because they're longer questions. Yeah, I would probably stray away from that. They would have to make it either incredibly easy or split it up into many different parts and then make you come to like an assumption at the end. Does that make sense?
Okay, thank you.
Yeah. Yeah, the only way to calculate actual max and min would be, yeah, it would probably be Lagrange multipliers, but it would be like a combination of that, which is kind of an important process there. Yeah, so the difference there that you're kind of talking about there, Nikki, is that if I want to find basically something like this, I guess, if I told you I have some function like f of xy is equal to x squared plus, let me actually do something a little bit better, x squared times y on my domain, x squared plus y squared is less than or equal to 1. Something like this here. And I want to find the absolute max and min on this. Right? I have to do two parts. I have to do this twofold. The first part is to calculate literally if there's any critical points inside this domain here. If there's no critical points inside this domain, I know that it can't exist, right? There can't be any maxes or mins inside there. And yeah, WebAssign, yes. So WebAssign, yeah, so absolute maxes and mins are only at critical points, really. I guess. Yeah, they're only at critical points. So absolute maxes and absolute mins, you would just then evaluate. I mean, I guess here, what you could do is you could calculate the function values here, here, and here, and then try to come up with an absolute max and min. But the thing is, you would have to have something that goes to 0 or have something that's a little bit more, I guess, that I guess asymptotes near the outside as x and y grow. Because other than that, it's very, very difficult because otherwise it's going to be infinite, right? Or it'll be negative infinity. So you have to have something that kind of smooths out at the end. But if I have something like this, where I have kind of a domain that's less than or equal to 1, I have to maybe see if there's any critical points here inside. So I just do this very generally. And then what I would do is I would use Lagrange multipliers to find the maximums on the outside. Because I know that in the same exact way, right, if I come up with an absolute max or min on a domain, the only places that it could occur are on the inside or the endpoint. In the same exact way, I have to also check the endpoints, which in this case would be the outside of my domain. Does that make sense? I think that's really the only time you would think about using like an absolute max here, in terms of at least an extreme value kind of case there. I don't know if you want to actually do the problem I came up with here. I think it's a fun one. I'm not too sure actually. but we can at least do this here, at least talk about Lagrange multipliers with this exact problem that I came up with. I think it's not a bad idea. So again, Lagrange multipliers here, what we do is, just in general, if I want to maximize or minimize f of x, y, this is the process I'll use here. I'll move over and kind of zoom in a little bit more. If I have f of x, y here, and I would like to maximize or minimize, I want to find the extremes. But I'm subject to a constraint. I usually have g of x, y is equal to k. This all extends also very nicely to, multiple dimensions, like x, y, z, whatever. What we do is we basically want to find where the gradients of f and g are parallel. That's the actual goal. And so what we do is want to try to find all the points such that the gradient of f is equal to, basically the gradient of g, but it's kind of a scalar multiple because we know that scalar multiples are parallel. So we kind of multiply it by some lambda. And we also are subject to this constraint here. And we just solve this system of equations for all x, y, and lambda. You don't have to solve for lambda. It's not necessary ever. Sometimes it's very, very beneficial to, and it'll help you out solve this system of equations. But sometimes it's just not necessary at all. And then what we do is we plug into f and see which is biggest, and then find the extremes. So the Lagrange multiplier method actually guarantees you, which is really important, it guarantees you that every point that comes up with the Lagrange, at least you will find this. There's actually one or two ways that it can break, but it's really, really complicated to think about that way. We're not going to think about that. This will never break for our problems, at least here. So let's at least talk about here where we have f of xy is equal to x squared times y. And I have x squared plus y squared is equal to 1. I'm literally on a circle of radius 1 here. So what we do, here's the process. We again define this as g of xy. I take the gradient of both of these. So I take the gradient of f here. The gradient of f is equal to 2xy and then x squared. This is one I just came up with. This might be really fun. We'll find out. I don't know. Gradient of g is equal to 2x and 2y. And so therefore, using the Lagrange multiplier method, we usually have lambda times g, which gives us 2xy x squared equals lambda times 2x 2y. And so if I equate the x components, I equate the y components here, I would get that this is 2xy is equal to 2 lambda x. And then I would get x squared is equal to 2 lambda x, 2 lambda y. As well, we have this constraint of x squared plus y squared is equal to 1. And so now we come up, this is our system of equations. And we basically want to find all the x and y that satisfy that. So as I kind of had mentioned, I think in a previous example, previous thing, you might want to always ask yourself here, what's the best way to solve these problems? I usually like to go for the fact that, at least here, I noticed down here that, at least in this equation, that I get x squared is equal to 2 lambda x. In this one, I have x's on both sides. Now, I need to be very careful because I can't divide out by x, or can I? That's something you should always check. Am I able to divide out by x? Because x could be 0, right? It could be 0. 0 could be definitely a value for x here. But you should always see if it breaks, if something does break, just in general. Because if it does, that means that you can maybe divide out by x or divide out by y or something like that. So if you notice here, if x is equal to 0, well, let's let x be equal to 0. I hope you agree that then y here gives me, this one right here gives me that 0 is equal to 2 lambda y. So y has to be equal to 0. And we note that x equal to 0 and y equals 0 does not satisfy equation 3. Right? So that means that x cannot be 0 and y cannot be 0. So we're all good there. So I can actually divide out by x if I wanted to, which is really nice. So here, what this means is equation 1 then gives me, if I divide out by x, this gives me that y is equal to lambda, right? It actually does, which is pretty cool. This actually gives me that y is equal to lambda. Because I could divide out by the 2's, I divide out by the x's, I get y is equal to lambda. Plugging this actually into 2 then, I can just substitute the y for lambda, which gets me that x squared is equal to 2 y squared. Right? That's what that gives me. And so lastly here, this is going to be that x squared is equal to 2y squared. Well, what I could do then is I could plug in 2y squared into for x squared for my equation 3 here. And so what I could do is I can get that this is 2y squared plus y squared is equal to 1. And now just solve for this. So we would get 3y squared is equal to 1. We get that y squared is equal to 1/3. And therefore y is equal to plus or minus 1 over the square root of 3. Or maybe more succinctly, you could write this square root of 3 over 3, plus or minus. Something like that. But it's kind of nice. So this tells me that y has to be either plus or minus square root of 3 over 3, or 1 over the square root of 3, however you want to think about it. And so what we do is we now take these points here, and we plug them back into equation 2 to get what x has to be. So take, for instance, we do y is equal to the square root of 3 over 3. Will imply then that x squared is equal to 2 times 3 over 9, or just 2/3. Right? I have to square it. And so this implies then that then x is equal to these plus or minus the square root of 2/3. So this then means that I have 2 points out of this. I can get that this could be the square root of 2/3, 1 over radical 3, or negative square root of 2/3, 1 over radical 3 here. That's what I can get it from that, right? Because I have 2 options. I either have that when y is square root of 3 over 3, I can get, both of these 2 x's. Similarly, we could do the same exact thing for when y is equal to negative square root of 3 over 3, which then gives me here x squared is again going to be equal to 2/3 because the negative will get removed here. And then from this point, we go from here and we get that x is equal to plus or minus the square root of 2/3, which again gives me, I'll get plus square root of 2/3, negative 1 over square root of 3. Now I get negative square root of 2/3 and 1 over the square root of 3. And so these are the points that could make positives or negatives. Now you might get some, you might get some extraneous solutions, which might just not work, and that's okay. The Lagrange multiplier just gives you all the possible options that would be extreme value.
For the last point, is that negative square root of 2 over 3?
Yeah, that's a negative.
Okay, thanks.
For both of them. Oh, for both, yeah, there's a negative there and a negative there. Yep, thank you. So then what we do is we plug these guys in to our function f, where we want to maximize. And I hope you'd agree then, we kind of plug all these guys in. So we find f of square root of 2/3, 1 over the square root of 3, f of negative square root of 2/3, 1 over radical 3, f of square root of 2/3, negative 1 over radical 3, f of negative square root of 2/3, negative 1 over radical 3. And plugging these in to this equation here, which is just x squared times y, we would get that this would be equal to 2/3 times 1 over radical 3, which this is just, we could also just write this as 2 over 3 radical 3. This one right here would be the exact same thing, because again, we're getting squared out of the x here. That's what's going to make this. And then what we could do, yes, we can just recognize then that this would just be negative 2 over 3 radical 3 here, and this would be negative 2 over 3 radical 3. Yeah, you can usually recognize that pretty quickly. They'll make those unique values. They'll only make either 2 over square root of 3 over square root of 3 and that, because the combinations of those will either be positive or negative at value. So your answer, if you were asked your answer specifically, if you're asked for your maximum or minimum, your max value is going to be 2 over 3 root 3. And it occurs at these 2 points. And your min value occurs at negative, when the points become negative 2 over radical 3, or 3 over radical 3. Here. And so if you're asked for the min and max values, you don't give me the points, you actually give me the function value specifically. There. As I think these Lagrange multipliers. This is a kind of a weird example that we did, but I hope you agree, I hope you kind of understand that you're not going to get asked a really complicated one on the exam. It wouldn't do that because these can get really, really tedious really quickly, honestly. And it can cause a lot of confusion because it's a lot of sometimes really, really complicated and really complex. I mean, I have a friend that actually does Lagrange multipliers for research and has to solve like 6, 7 variables at a time, which could cause really, really tedious as you could might have imagined. Yeah, so that's at least that part. Does anybody have any questions about Lagrange multipliers here? Any other questions I can clear up in this case? We're actually unfortunately running out of time. But does anybody have any questions about this here? Okay. They may have just more general questions. We have about 3 more minutes or so here. I'm going to post this whole video on YouTube, so you can either watch this again or if you want to go back to any certain part, or I'll even post the whiteboard too, so you can go back to it too on that. It just have any general questions I could answer. Tomorrow's session starts at 5 to 7 tomorrow. Yep, 5 to 7 tomorrow, and then 4 to 7 we're doing a 3-hour fun review session on Wednesday for last minute stuff. The exam's 2 hours. Any other questions here I can answer? I hope you guys are doing well. We're staying sane. Yeah, it's kind of weird not being in class anymore. I haven't taken class. This was my first year ever. I've never really taken class, so it's kind of just strange to not be in the academic. But I know how hard it is, especially during finals week. Yeah, so I guess that's it then. If nobody has any other questions, feel free to post on Piazza. Your TAs/teachers should have posted the exam answer keys. If they haven't yet, please reach. Well, they're on. DJ did. I think they're also on Piazza as well. So feel free to just go ahead and look at them too. I'm happy that he did that. And yeah, I think that's it for me here. Unless you guys have any other questions, I'll stick around if you guys have any just general questions for me. And yeah, I hope you guys have a great night. And I hope you guys are doing well. I'll stick around though.
Thank you.